Hello, everybody. Welcome to this edition of the ICTS String Seminar Series. Today, we have the pleasure of having Biswajit Sahoo with us, and he's going to talk to us about classical soft graviton theorem and gravitational memory. Take it away, Biswajit.
Okay, thank you. Thanks for inviting me. And so today I'll talk about like classical soft graviton theorem and gravitational memory. So let me first give a outline which I'm going to talk about. So my talk will be divided basically into 5 parts. So first, I will briefly review the soft theory results of the soft theorem in space-time dimension greater than 4 and in space-time dimension 4. Then also I will talk about the classical limit of soft theorem. Then in detail I will discuss the classical soft theorem basically on the soft graviton theorem part and also how it is related to gravitational tail memories. So let me first tell so all the things which I'm going to talk about, there is always counterparts in case of like soft photon theorem or electromagnetic memory, but like I will not talk about this thing in my talk, and only like if some question arises then I will go back to these parts. And let me also tell how this all this works fits fits in a bigger program which started by like trying to extract the gravitational waveform starting from the scattering amplitude what we learned for like particle scattering, and how much can we extract from our learning of the scattering amplitude and try to relate it to the gravitational waveform. So this is a like bigger program, and all this works fits in that program. And for a moment, if we just consider a simple example of like black hole merger process, where like there will be gravitational radiation will be produced, and like one tries to determine how the gravitational waveform will look like. And here a sample example is given when the two black holes are like large apart and they are inspiraling. At that stage, like one uses post-Newtonian analysis to derive the gravitational waveform. And when they comes very close in the merger phase, like one needs to use numerical relativity, because like the gravitational strain is very strong. Perturbative approach or any approximate approach will not work. Then after that, after the merger thing happens, when there will be ring down phase, and that ring down phase, to analyze the ring down phase, one use the black hole perturbation theory. And finally, what I'm going to talk about is that after this ring down phase, one can still observe the gravitational waveform, the behavior of the gravitational waveform at large time, and that is related to gravitational memory. And what I will talk about is basically soft theorem will give input to derive this gravitational memory. And what is gravitational memory? Like I will talk about these things later, but this is just a brief picture what I am going to talk about. So then, so basically I will talk about some of the works which I have worked with Ashok Sen, Arnav Priya Saha, and recently I am working with Devodinno Ghosh. So let me start with a brief review of soft graviton theorem in space-time dimension greater than 4. So what is soft graviton theorem in terms of scattering amplitude? So consider an amplitude with arbitrary number of finite energy particles, which we will call hard particles. These particles can carry also massless gravitons with who have the energy of the gravitons are large. And these particles can have arbitrary mass, can have arbitrary spin, and also this scattering amplitude has some small energy gravitons as external states, which we will call soft gravitons. And if we start with this amplitude, we can show that this amplitude we can relate to an amplitude which does not carry these soft gravitons. And this relation is via expansion in power of the soft momenta, which is soft momenta is basically the momentum of the soft graviton. So for one simple example, if we consider a amplitude, which is I'm relating denoting by gamma n plus 1, which is n number of finite energy particles and one soft graviton, and this soft graviton has polarization like epsilon and momenta k, and the finite energy particles have momenta pa and spin sigma a. then this amplitude we can relate to a amplitude which you can see the n particle amplitude, which only now carries the information about the finite energy particles moment and spin. And this relation is through power series expansion in the energy of the soft graviton, which is omega, which I'm denoting k to be omega times the the direction, like the unit null vector, which is defines the direction of this soft graviton emission. So then one can show that one can expand this amplitude and can relate to the amplitude of endpoint amplitude, and these factors which are sitting in front, those are known as the soft factors, and those are can be some multiplicative numbers or can be some differential operators as well. So this S0 is known as the leading soft factor and subleading and sub-subleading soft factors. And if we try to see what is the power when omega going to zero limit, omega is the energy of the soft graviton, then S0 goes 1 over omega, S1 goes omega to the power 0, which is order 1, and S2 goes order omega, and another in such a way. But this result what I am going to talk about are true for loop level, for the full amplitude in only d greater than 4, and this is true in d equal to 4 only at tree level. But loop level there will be correction, which I will discuss later. So this is the basic picture of soft graviton theorem, and let me give a diagrammatic understanding how one can derive this soft graviton theorem. So suppose we start with a theory which is completely general coordinate invariant theory, and another the theory is given in terms of a one particle irreducible effective action. Then to derive to compute any amplitude, only we need to compute only the tree level amplitude starting from this 1 pi effective action. In a sense, if we want to compute this n plus 1 point amplitude, which is given here, where the red line is denoted by the soft graviton and the black lines are basically the finite energy particles, then this amplitude can be written as a sum over two kind of set of sub diagrams. At the first kind of diagram, you can see when the soft graviton is attached to any external leg via a 3-point function, which is through finite energy particle and one soft graviton. And on the other hand, another kind of diagrams where the soft graviton is rest of the diagram where the soft graviton is not attached to any external leg. So you can see what is the advantage when the soft graviton is attached to a external leg. It appears that it has a propagator with momenta pa plus k, and if it has a propagator with momenta pa plus k, then using the on-cell condition of the finite energy particle, it goes 1 over 2 pa dot k, and since k goes omega, so it contributes to 1 over omega. On the other hand, when the soft graviton is attached to any of the internal lines or vertices, then it appears that it does not contribute to, it don't have a propagator, so it start contributing at order omega to the power 0 in the small omega expansion. But all this statement what I am making, this is based on the fact that this gamma n, this gamma tilde n plus 1 or this gamma 3, they don't contribute as 1 over omega or any power of omega in the denominator. So this is kind of a assumptions of locality, but this may be true for a usual given action, but may not be true for a one particle irreducible effective action, and this will be a problem in d equal to 4. One can show that in d greater than 4 this statement is true. That's why this covariantization prescription which basically derives these vertices and this gamma tilde n plus 1 starting from the 1 pi effective action and basically covariantizing in the background of graviton, that works. So this is basically basic picture, but I will not go to the detail, but just to give the result. So what happens is that if we start with this prescription and try to derive the soft factors, here I am giving the result, this gamma n plus 1, the n plus 1 point amplitude, and that the S0, which is I talked about the leading soft factor, goes omega 1 over omega, that has the structure the polarization tensor contracted with the finite energy particles momenta over pi dot k's. And this epsilon I transpose is basically the polarization tensor for the finite energy particles. For a moment we can ignore this part. And then the subleading soft factor, which I am denoting by the S1, which has the structure, you can see the similar kind of structure like the leading soft factor, but one of the pi will be just replaced by the k times the total angular momenta, where you can see the pi del del pi factors at the orbital part, and this is the spin and part of the finite energy particles. So this is like this. So this subleading soft factor depends on the like total angular momenta of the initial and the final particles, and also the polarization of the graviton and its momenta. And also, if one try to go to the sub-subleading order, one can show that at the sub-subleading order also this factorization happens, and in the sub-subleading order it is basically quadratic in the total angular momenta. But in the sub-subleading order, it turns out that there is some non-universal piece appears, like which one can think of as like the like in the effective action one can add some non-minimal coupling, which in terms of the Riemann tensor of the soft graviton field, and that basically can contributes to the non-universal piece, but the structure is completely fixed at the sub-subleading order. And what happens is that after this order, like suppose one want to go to the subcube leading order, it turns out that it is not quite known that whether this even this gamma n plus 1 at this order can be written as a factorizable form in terms of the gamma n. So this is like still unknown for a generic theory, and how to proceed this is not known. So up to now, is there any questions? Okay.
I have a question. So what about general relativity? I mean, is it known not for generic theory, but just for general relativity, minimal coupling, and then what happens? Is it still factorizable?
Yeah, like that is what I'm going to say next. Like for a simple theory, like consider like scalar coupled to GR in a minimal way, how much can one derive after this order? So one can show that some part of it can be derivable, but still some part still remains, and it is not clear whether that part could be derivable or not. So I'm just going to talk about next. So suppose like this is what I'm going to talk for a general case, like generic theory, but consider simple theory, like simple theory like scalar coupled to gravity, and also consider that, okay, like focus on only tree level amplitudes for simplicity. So how much can one so that this factorization can be held? So this is actually attempted by two papers in 2018, and like they use basically the gauge invariance to fix that how much can one derive to the sub to the power n leading order soft factors. So like here you could just think of this gamma n plus 1 are basically some like tree level like some tree level diagrams, like no loops are involved. And so here I'm drawing again dividing it into two parts. One is when the soft graviton is attached to external leg, but now no one pi vertex. This is just a like minimally coupled vertex. And then this is also when the soft graviton is attached to any of the internal leg or vertices. Then what happens is that, okay, so let's start. So just from these diagrams, we can see how the structure of this gamma n plus 1 will look like. So you can see due to this graviton is coupled to the scalar line minimally, so there will be a factor of pa mu pa nu by pa dot k. This just follows from the minimal coupling. And then there is one amplitude gamma n, but one of the momenta is not pa but pa plus k, and then this graviton can attach to any of the legs, so sum over a. And the rest of the diagram which we don't know how to evaluate, so let's just denote it by gamma tilde n plus 1 mu nu contracted with epsilon mu nu. Okay, then let's expand these factors in power of a. So suppose like we assume that there is a power series expansion can be happen like is true. So we just expand in a Taylor series expansion in omega going to 0 limit, and then we can write it down in expanded form. And this term can be expanded, and this term we don't know how to expand, so we don't know whether it can be related to gamma in amplitude. So just with some arbitrary constant r, just with the coefficient of the Taylor series expansion. And then let's use just the gauge invariance to fix that how much we can fix the coefficient r in terms of the factors coming from the first kind of diagrams. And if one do that, it turns out that really one can proceed a lot. Like one can write down, suppose this like the sub to the power n leading soft factor turns out to be a form that which is basically, like you can see, this is like a sub-leading soft factor, only the orbital pieces, and then like some k alpha del del p alpha whole to the power n minus 2 operating on the n point amplitude, but still some part still remains, and one can show that this part cannot be fixed just from the gauge invariance. And like what happens is that, so this part is self gauge invariant, like gauge invariant by itself. And like this r, but the only the thing is that the r have to some property which is like antisymmetric under like the two in mu and the other alpha indices, and nu and the other alpha indices if we exchange. So this is how much is known, like in like you can think of like d greater than 4 full amplitudes, or like d equal to 4 only tree level amplitudes. So this is how much one known, and one cannot fix this r. But like possibly like for a like two going to two scalar particle scattering, if some graviton is attached and it is minimally coupled, one can possibly fix this function r. But like just from gauge invariance it is not clear how to fix it. And like yeah, this is what in literature what is known till now. But this structure will be important for me, so when I'll go to talk about later. So just keep in mind the structure, how it look like. Okay, so this is the story what I wanted to talk in d greater than 4. Then let me go to the status of soft theorem in d equal to 4. So here also I will not go too much in detail, but tell the main ideas.
Hello?
Yes.
Yeah, sorry. Can I just ask a question? So, let us say we look at 2 to 2 scattering
Right.
of just, I mean, we can just even take all of them to be gravitons.
Mm-hmm.
One of them soft, the other things are hard.
Right.
Do we understand, like the full expansion in that case? Because at least, like all these tensor structures are all classified, right, in some sense. Like,
Yeah, I know.
So, like, do we understand how the soft theorems work in that case?
Yeah, like yeah, I understand your question, but like I think it has not been analyzed like in detail. And what can happen is that this r may not be written in terms of some operator operating on this gamma n. So like it can happen that that's like the soft theorem tells us that how to relate gamma n plus 1 to gamma n, and it may not happen that these extra factors are that it cannot be written in like some operator operating on gamma n. That can happen, but yeah, I think since the tensor structure are known and classified, like possibly like one can write.
Hi, yeah.
Because this is a question only about 4-point functions and 3-point functions.
Exactly.
Yeah, which is just a small remark actually for the, I think Loga is asking for pure gravity, right?
Yes.
So that photon amplitude is either MHV or anti-MHV. Everything else vanishes. And there it is known that it will factorize into a soft factor times just the MHV 3 point.
Yeah, so I meant pure gravity, but not general relativity. If I mean.
Yeah, no, I'm saying that there it is known the factorization to all orders in the energy because it's just MHV or anti-MHV amplitude.
But Alok, that statement is true for any pure gravity, not just general relativity. Even if you have high.
Oh, sorry. No, I just meant for GR. You're right.
Yeah. But Alok, is it known for higher point amplitudes, like
yes,
not
for MHV
to
is
3,
known.
but okay.
For MHV, the factorization is known. For 3 level MHV,
okay.
It's the exact factorization irrespective of the energy.
Okay.
That's a statement about general relativity.
Only GR.
Yeah. Okay.
Okay. Thank you. Yeah, I was not aware of.
But I thought even for higher derivative things, all the structures are classified now for 3-point and 4-point functions. So in principle, one can write down the more general 4-point function and take a soft limit and ask at some order, is it some operator times some structure appearing in 3-point function?
Okay.
Shouldn't that question have a yes or no answer? I mean, is there some obstacle that I'm not seeing, or is it just not done?
Okay. Yeah. Okay. Like possibly like yeah, I have to look it in a more careful way. But yeah, this is what like is known in literature currently. But yeah, possibly one can progress on it. Yep.
Okay.
Okay. Now let me talk about like the soft graviton theorem in 4 space time dimension and why it is so special. So the first problem is that like the gravitational S matrix is IR divergent, like infrared divergent. So like when we are going to talk about soft theorems in terms of S matrices, and the S matrices are IR divergent, so like this, how to make sense this is the question. And but the thing is that soft theorem is the relation between two S matrices. So like even if they are individually IR divergent, can we remove the same IR divergent pieces from
呢個係一個 scattering 入邊好重要嘅概念嚟，譬如好似喺J.J. Sahoo Chapter 7入邊，喺呢一個George 嗰份。
Sorry, I can't understand.
Sorry, was there a question? I didn't get the question.
Yeah, I also didn't get.
Yeah, maybe you can continue if there's a question. Maybe we asked again.
So, so what I was talking about, that like the soft theorem is a relation between two S matrices. So even if individually they are IR divergent, can we remove the same IR divergent pieces from both the S matrices, and then we can extract out the soft factors. So this is like the approach, and this is also kind of the approach like one uses in the iconal factorization process. Like let's consider the n+1 point amplitude, and we will try to write as some like exponentialization of the IR divergent pieces time a IR finite amplitude. And similarly, if we try to write down this n-point amplitude as a some exponentialization of some IR divergent pieces time a IR finite amplitude, so then like just like we can cancel, like if the IR divergent factors are same for both sides, then we can just cancel the IR divergence pieces and try to relate the IR finite pieces and try to do the small omega limit and extract the soft factors. So this is what we want to do, but just let me try to explain that if we try to do it for the case of gravity, it turns out that gamma n+1 point amplitude has some extra IR divergent pieces relative to this gamma n point amplitude. And then basically it turns out that even after some cancellation of the common IR divergent pieces, some extra IR divergent pieces remains, and that one have to IR regulate to extract the soft factors. And let me tell, so in like notations, I am denoting this KGR is basically the like the exponential factors, though I have not given the explicit expressions. But it turns out that if we take the if we take the loop momenta going to zero limit, then basically this KGR factor basically reduces to the non-iconal factors, like what non-iconal factors for the like gravitational scattering process, which is known. And this K phase factor, this is just nomenclature K phase, it basically tells us the same iconal factor, but now when the like the virtual graviton is running between the finite energy particles and the soft graviton. And so this is why this is extra in gamma n+1 relative to gamma n, but for QED case there is no such extra factors and it works perfectly. So, and to like this factor, to factor out these IR divergent pieces and exponentialize it, we use basically we use the Grammariani technique, which is developed for quantum electrodynamics in 1973, and we generalize it for the gravity case. And then basically what we want to do is basically we want to relate this gamma n+1 g, which is the IR finite piece of the amplitude, n+1 point amplitude to the IR finite piece of the n point amplitude, and basically try to extract the soft factors. And how far we have done is only up to the subleading order. So the key strategy of this like factorization of this IR finite and the IR divergent pieces is basically what we have done is basically if there is some virtual graviton propagator, we basically split it into two parts. One we'll call K graviton and another is G graviton. Here I am denoting this K and G. And what we want is that if we compute a diagram with the K graviton propagator, that should contain the full IR divergent piece, and may contain some finite piece, but that we can like using our prescriptions, we can what we want we can do that. And the another thing is that if that implies that if we compute a amplitude with G graviton propagator, that is completely IR finite. And also the another requirement is that the K graviton propagator which we choose, that we have to choose in such a way that this factorization of these IR divergent pieces holds for both n particle and n plus 1 particle amplitudes. So I'm not going to give you like the details, but if we use these prescriptions, it turns out that if we want to derive the subleading orders of factors, then it turns out that only like analyzing one loop amplitude is enough, like the kind of diagrams which I am giving here, like for consider like scalar coupled to gravity. This is the theory, and basically we have to compute like 5-point roughly, like if you want to relate to 5-point amplitude to 4-point amplitude, then you can see that basically we have to compute like the 5-point amplitude with 4 scalar and 1 graviton and like only the one loop diagrams. But what happens is that since we already removed the divergent pieces, so only the IR finite pieces are remains. So basically the virtual gravitons are basically the G gravitons propagator. And the other kind of diagrams which I already mentioned you that when that contains some extra IR divergent pieces which involves like the 3 graviton vertices, they have to be evaluated with the full graviton propagator by using IR regulator. And basically if we try to analyze these diagrams, we see that at subleading order, the omega going to 0 limit contribution is not omega to the power 0 but log omega, and the coefficient of this log omega looks like these expressions after the evaluation which I have written here. And just I want to mention one point is that you can see this coefficient is fully determined by the asymptotic momentum of the incoming and outgoing particles, and don't depend on any other information how the scattering happens and anything. And the other thing is that you can see each of this expression contains a 2 particle sum, and that is like clear from these things because like there are always like this is like this log omega terms contributes when there is some virtual graviton is running between 2 particles. So there is always like a 2 particle sum in the contributions. And another thing is that the first 2 line you can see is basically this eta b symbols which I am denoting. They are +1 if they are outgoing and -1 if they are incoming. So when both sign, like when multiplication of eta b equal to 1, that means either both particles are incoming or both particles are outgoing, then only these first 2 lines survives. On the other hand, the last 2 lines are non-vanishing for even if one particle is incoming and the other particle is outgoing. So, but the thing is that this looks like little complicated, but if we can try to rewrite it in terms of the same like factors which I denote this kgr and k phase in the simple way. So one can show that this like the log omega coefficient can be written as the k phase term, which is the iconal factor due to the virtual graviton running between a finite energy particles and the soft graviton. If we regulate it in the integration range when the loop momenta is smaller than omega and greater than the IR cutoff, and the kgr regulated, which is basically the same kgr factor, the iconal factor, when the virtual graviton is running between 2 finite energy particles, but now regulated with the momenta which is greater than omega. And you can see now that this log omega coefficient can be written just as the k phase factor times the d greater than for leading soft factor, and the other term is basically the tree level subleading soft factor operating on the same iconal factor but regulated in this range. So this is just rewriting of the earlier result which we derived analyzing one loop analysis. And here I have given the expressions for this kgr regulated and the k phase regulated pieces. And just want to notice that this integral is basically, you can see like it is like the Feynman propagator for the graviton 1 by L square, and like the 2 propagator of the particle A and the particle B piece. And this is the general structure. So why I'm rewriting in this way? Because like you can see, like now suppose like we forget about everything, the derivation, how we make it IR finite and anything, and try to understand how this result can be derived just from the case. So suppose like we naively assume that okay, like whatever we derived for d greater than 4 soft theorem is also valid in d equal to 4, but in the loop momentum range, which is the regulated range which I mentioned earlier. Then okay, then we write down okay, like say full gamma n plus 1 is written as the d greater than 4 soft factor operating on gamma n. Now we have seen that in regulated range of integration, gamma n plus 1 can be written as exponential of some phase factor like k phase, which I denote, and exponential of this kgr. And on the other hand, gamma n is written as only exponential of kgr, but all are in the regulated range of integration. And this k factors, like the k phase factor behaves like omega log omega, and this kgr regulated which goes like log omega. And if we just substitute this expression in the expression and just like the expand in power of omega and commute through this differential operator, these exponential factors, we get back the same subleading soft factor which I have written here. So this gives a like naive understanding that possibly like whatever we have done in d greater than 4, they will analysis, this will be still valid in d equal to 4. But if we regulate our like the integration range in the range I prescribed earlier, and then just commute through this differential operator, we still can derive the soft factors. So this is just a observation, and if this observation we like consider that this is true, possibly like we can also like try to use this observation to like conjecture the higher order results.
佢係陷入咗一種，佢陷入咗真係唔知點解喺坐標系統幾何空間向量空間嘅結構分量基底卻 index 嘅 structure variable 嘅 reality condition 分析學上面不必要嘅嚴謹性 measure 嘅 notation 本質係初等嘅 subject 可能就有呢啲問題。
Hello, I can't understand. Is there any question? Should I proceed?
Sorry, I think I was muted. So you probably couldn't hear me. No, I was just saying maybe you should go ahead. I don't know if Hanpai just has his mute mic on by mistake or something.
Okay. So maybe you can mute him so that.
Yeah, I've muted him for now. Maybe if he has a question, he can unmute himself and ask.
Okay. So yeah, so like if we try to like now generalize this observation to higher order, like we can conjecture that at sub-leading order how the like sub-leading order soft factor will look like. And just like basically if we like again do the same thing, that we start with the like up to sub-leading order, how the amplitude how the gamma n plus 1 will look like, and just write as up to the sub-leading order soft factors, and then use the same prescription. From there we can also conjecture that how the omega log omega square terms will look like, and you can see that will be just like the k phase square times the leading soft factor, k phase times the sub-leading soft factor, like sub-leading soft factor operating on this kgr, and again the sub-leading order when the orbital parts are operating on this kgr regulated pieces. And like this is only the omega log omega square term at the sub-leading order, but like one cannot say anything about the omega log omega square, but one cannot say about anything about the omega log omega pieces. And like if we try to derive it, so it has not been derived from diagrammatics, but if one want to derive it from the like the amplitude thing, then basically one can use the same Grammarian technique which we have derived, and one have to analyze the two loop amplitudes to derive this result. And its classical counterpart has been now derived, and I'll discuss in the end. So like now, like if we are bold enough.
Biswajit?
Yes, sure.
Yeah. So somewhat, like a side question. So these IR divergences, like, do they show up, like if you kind of are looking at some of these other things that people talk about, like post-Newtonian expansion or post-Minkowski expansion and so on and so forth. Like is that like what I'm asking is that or in the potential, does it actually like can it be compared against something that is known, or is that especially the two loop prediction that you're making, or
Oh, actually, like we compared this result in the massless scattering limit. So in the massless scattering limit, there is this Veneziano and his collaborators. They considered 2 going to 2 massless graviton scattering in n equal to 8 supergravity, and for them, like they have a omega expansion, and they also have this omega log omega square terms also. And in the massless limit, like it agrees with their result.
So this is 4D n equal to 8 supergravity, 4D maximal supergravity.
Exactly.
In 2 loops.
2 loops. Yeah,
Is
recently we wrote a paper where we get given exact matching with this result, and also like there are some there are some factor problems in their paper, so we fixed this issues also. Yeah, using this subleading term.
Okay. So just to make sure that I'm understanding what you're saying. So you're saying that if you compare it against n equal to 8 in where you have other massless particles and so on, you
Right.
get like a quantitative match. You get all the factors, all these.
Yeah, exactly. Like this also tells us that this factor is like completely universal. Like it won't depend on like if there are some other like high derivative characters or other massless particles and other things also. Yeah.
Okay. Thanks.
Yeah. So now, like this
Sorry,
is like
just one more thing. Just the thing that I was asking, like, is there some so many of these, like gravity amplitudes people have used, Weber and various people have used
right.
to kind of go, like make contact with the kind of thing that people in general relativity do, right? Like this is what I was asking about the post-Minkowski expansion, for example.
Right. Yeah, I think.
Like,
I think
this,
what happened. Sorry, yeah, I think what happens is that most of their computations are like not the radiation, like correction to the effective potential, this kind of calculations they are doing, not really extracting the waveforms
yes.
or like that. So so that's why like for the conservative kind of systems, like I don't know how to compare, but there are some computations which talks about this, trying to extract these gravitational radiations, like the one which I'm talking about, Veneziano and his collaborators have derived. So there we compared up to this order, and it agrees with their results.
But the same IR divergences should show up even in the conservative case, right? When you have loops and so on.
So like what happens is that the same IR divergences will show up there, but the physical quantities what they compute, suppose correction to the effective potential and other things, they are like this IR divergence are not affecting. They are somehow cancelling in the intermediate space. So the physical quantities are not being affected by these IR divergences. Like here also, like we try to derive the waveforms, and we can see that IR divergences are not affecting our gravitational waveform up to some order in omega expansions.
Okay. You're saying, like it's like the analog of, if you're calculating some inclusive quantities or IR safe quantities, then, like they don't show up. So it's not easy to compare IR divergence structures. Is that what you're saying?
Yeah, it's okay. Yeah, somehow what I am trying to tell is that if you want to compute any physical observable quantities, those are not being affected by the IR divergences, and like somehow in the like the intermediate steps they are appearing, but they are not affecting the physical quantities which one want to compute. But yeah, to direct compare with their conservative calculations, like the potential correction to the potentials or other things to these radiation pieces, yeah, how to compare it, yeah, I am not sure about that.
Okay, thank you.
Sorry, Biswajit, don't they also compute the corrections to the radiation, not just the potentials, but also
I think like they take
radiation
care about
reaction?
radiation reaction, like due to the radiation, like due to the leading order radiation, what is the back reaction to the potential that they have computed. So the computation
I
is
see.
taking the potential, but how the radiation is taken, like the radiation back reaction effect on these potentials has been taken care of as far as I know, but yeah.
I see.
Basically,
Right.
just a small comment that in the Burns work that Loga was asking about in the conservative sector,
Right.
the loop momenta that contribute are such that the spatial loop momenta are the order of the impact parameter. It's the potential region that gives the dominant contribution.
Right.
In your case, it's the much like IR sector, right? Loop momenta is much less than the inverse of the impact parameter that is giving this contribution. So the contributions are coming from different regions in the loop momentum space, right? So
Okay, but yeah, I agree. But I think like recently now they also have like gone from the potential to the radiation regions.
yeah. I was talking about the earlier conservative,
Yeah,
right?
the earlier conservative, yeah, this is different regions, but recently like they also taken care about the radiation regions, and also that's why they got also the radiation back reaction
Okay.
corrections. Yeah, right. Yeah, but yeah, I really like don't know how to compare it with their results. Okay. So let me next tell you like so this is like very speculative thing that like if we try to again like generalize this stuff to the sub to the power n leading order, how it will look like. So again, like you can like if we just consider the like the sub leading the sub to the power n leading term which I like told earlier for the like very specific cases like scalar minimally coupled to gravity. So in that case, if we just try to see that okay, this is the result, we believe in t equal to 4 and use the same kind of argument which is the key observation which I mentioned, and try to write down how the sub to the power n leading order sub factor will look like. So one can show that this will have this similar kind of the kind of structure just follows from the same observation. And like one can show actually that actually like this like one can at least like for the quantum electrodynamics cases the similar thing happens at the subcube leading order, and there also we derived the explicit form of this unknown r term which also contributes to the like omega to the power like omega to the power n minus 1 log omega to the power n order. Like here the sub to the power n sort factor at leading omega going to 0 limit will have the behavior omega to the power n log omega to the power n minus 1 log omega to the power n, and like the coefficient r which is unknown, like the unknown non-vanishing coefficient for the soft graviton theorem will start from the subcube leading order which has not derived, but for the QED case, it starts from the sub leading order, and we have explicitly derived this unknown coefficient. And so like we can say that like the factorization will hold at least for the leading non-analytic order at the sub to the power n leading order, even for the soft graviton theorem. And this is like the structure how it will look like, but still this R is undetermined, and if you want to determine, then one have to do the n loop analysis to derive this R factor, which is the unknown. But the structure will look like this, that like at least up to some order computation will suggest. So now let me summarize what we have what we have talked about now. So like what we are expecting is that like if we do a tree level analysis in d equal to 4, it gives the leading soft factor 1 over omega, it gives omega to the power 0 order omega, these are known. And at one loop order we got a log omega correction, and from two loop we will expect that the contributions at the leading order goes like omega log omega square. And similarly, n loop it will go like omega to the power n minus 1 log omega to the power n, and then there are some subleading corrections. And what I want to tell you here is that at each of this order, the leading non-analytic terms turns out to be like the structure turns out to be completely determined by the momenta of the incoming and outgoing objects and the information about the soft gravitons, but not the details and not how it is non-minimally coupled and other things. And the other thing is that like at each loop order, suppose one loop order I get log omega, it don't receive corrections from any higher loop order. So like the first column are completely like whatever loop order we determine, it is exact at that loop order, it is expected, but the next orders are not. And just I want to mention one point is that if we want to like scatter like spinning particles, then it turns out that for this like the spin of the when the spin of the particles are there, it turns out that at one loop order it starts contributing at order omega log omega order, but this is not the full result of omega log omega, because like at the two loop order also there is correction omega log omega which is expected to be non-universal, and that will also add up with this omega log omega contributions. So but like possibly like if we just try to give a result at one loop result which receives correction from two loops and other things, we still can derive this omega log omega terms for the spinning particle scattering cases. And so yeah, So let me see the time. Okay. Now let me talk about the classical limit of soft theorem. Okay, so the classical limit. So I'll since I'm a little bit of time, so let me tell that the classical limit of the soft theorem basically starts with like the multiple soft graviton theorem, and then consider that okay, large number of soft gravitons need to emit so that we can declare that as a the classical gravitational wave. And if we demand that, then it turns out that the scattered object have to be mass or energy which is large in the unit of the Planck mass. And also, since we want that the radiation energy has to be less than the energy of the finite energy particles, that seems to be like we have to scatter in a large impact parameter. But actually, this can be relaxed if we take care of the gravitational radiation also as a inside the finite energy particle sum. And if we try to do this, so this is Ladha and Sen, they derived that actually in this classical limit, one can relate the time Fourier transform of this gravitational waveform turns out to be proportional to the soft factor, like the classical version of the soft factor. What is this classical version I'm going to talk about? And this normalization is fixed, and this relation is true only up to some phase factor, because like this relation is derived comparing the energy of the soft gravitational radiation and on the other hand side from the classical waveform, and this energy has a mod square term. That's why up to phase this relation is true. So what happens is that, so let me, in d equal to 4, this relation will take the following form. So this is the E alpha beta, you think as like the deviation. E alpha beta is the trace reverse metric fluctuation, which is if you consider like the h mu nu to be the deviation from the metric, then the E alpha beta is the trace reverse part. And if you make a Fourier transform in the time variable and contact with the polarization, it turns out that will be 1 over 4 pi I times r. R is the distance from the scattering center to the detector, times some e to the power I omega r plus some undetermined phase times the classical soft factor. And like up to the subleading order, this classical soft factor will be this leading soft factor and the subleading soft factor. But now this orbital plus spin angular momentum, it will be replaced by the classical total angular momentum. This classical total angular momenta have to be determined like with the classical spin of the scatter object and by their classical trajectories. So this is how the how the classical limit of the soft factor looks like, which basically tells us that this relates the waveform to the soft factors by this relation. Now like if we consider that okay, like this is true in d equal to 4, so the derivation is done in d greater than 4. But if we try to consider that this is true in d equal to 4, and now what happens is that in d equal to 4, the asymptotic trajectory of the particles are not like they are moving with constant velocity, but they will have some logarithmic correction, where sigma is basically the like if you try to, sigma is the proper time or any affine parameter defining the trajectory of the particles. Then it turns out that the trajectory will receive a logarithmic corrections like log sigma. And then like if we try to just substitute in the classical orbital angular momentum piece by the trajectories, which is I have written here, then it basically looks like it also have a log sigma corrections. And now if we take sigma to be infinity, it seems that the classical orbital angular momentum diverges, so possibly the soft factors diverges. But we know that independent like gravitational waveform computations, we know that like the gravitational waveforms are always finite because we measure them anyway in LIGO and other gravitational wave detectors. So something is going wrong. And if one try to look it carefully, it turns out that actually one cannot, like if one want to derive the gravitational waveform with frequency omega, then the only contributions coming from the trajectory of the particle when the sigma is less or in the order of omega inverse, but not after that. That means there is a there is a cutoff for the sigma value, which is omega inverse, which suggests that one have to replace this log sigma by log of omega inverse. And if one do that, one can read of the subleading soft factors, how the classical subleading soft factors or the classical gravitational waveform will look like up to subleading order. And here I'm just giving the expressions for this Ca alpha, which is basically the coefficient of this log sigma term. Just one can derive it solving the geodesic equations. And the observation is that this Ca times this log omega inverse turns out to be exactly the momentum derivative of the like the KGR which I described earlier, but only the classical part. So this classical means basically you have to replace the Feynman propagator by the retarded propagator in the KGR expressions which I have given earlier. So like it tells us that the acceleration due to this long range force is also related to basically this iconal factor and the derivative of the iconal factor. And here I have given the iconal factor, but now replacing Feynman propagator by the retarded propagator. But this is not only the fact, but also since the graviton is emitting, so it also feels a long range force. So one have to also take care of the correction to the trajectories of this like gravitons as well, and that also relates to the like the backscattering effect. And if one takes care of all these things, then one can write down like the subleading correction to the gravitational waveform, which is written here. Again, you can see this is basically what we have given as like the subleading soft factor, but now I just replaced all this k's with a classical superscript. This classical means one have to evaluate this k in the regulated range, but replacing the Feynman propagator by the retarded propagator. And this is the structure how the gravitational waveform will look like in like omega going to zero limit. This is the subleading soft factor. But now we can use this observation and try to conjecture that like how the subleading order soft factors will look like, and also like using the same observation that the correction to the trajectory, the acceleration part will be just the del PMU of this KGRCL. One can conjecture that at the subleading order, the omega log omega squared terms have the following form of the waveform. And like this is now has been proved, but this is just I'm making the conjecture just from the classical limit of the soft theorem. And also one can go to derive the spinning case. Sorry. Okay, I was talking about now here the spin dependent pieces. So one can again start with up to the subleading order soft factors and try to derive the spin dependent gravitational memory, which I was talking about at order omega log omega order, and can use it to read of the spin dependent gravitational memory, which has the kind of following structure which contributes as omega log omega. But as I told earlier, that this is not the full contribution, this is only the order g square contribution, so it receives also correction from order g cube. So this is not exact at this order, but like at least like one can derive this one, we expect to derive this result considering the like the scattering of the particles carries spin. So this is like we are trying to do it now.
Sorry, Biswajit, just one question on your last slide.
Okay.
Or the slide before that, actually, you said that this expression you are getting from like you just explained, you make this assumption that you can put in these classical KGRs inside.
Right.
But you said this is also verified. How?
No. So yeah, I think like this is currently we are trying to derive it the spin dependent pieces. So I was thinking this is the subleading order piece. The subleading order pieces what I talked about, that is derived now, the omega log omega square order. But this omega log omega order, which I am like starting from this expression, I'm just giving here. This has not been yet derived, so we are currently working on it.
Okay. Thank you.
Okay. So yeah, how much time I have? Possibly like I am already
no, I think you started off almost 10 minutes after time. So
okay, thank you.
Fine.
Okay. So yeah, now like let me come to a systematic study of the classical soft graviton theorem. So up to now I talked about like the soft theorem from the S matrices, its classical limit, and try to give some conjectures. But like how can we derive this gravitational waveform directly, analyzing analyzing a classical scattering process. So the setup which we are going to
hello. So basically, sorry, before you proceed. So regarding this conjecture about the spin dependent piece,
right?
I was just trying to understand like what is the like what like is there some way that this kind of is relevant for some of these things where you have like spinning black holes and so on,
Exactly.
which much I mean, can you comment on what is the relevance and what, like how does it?
So like what happens is that, like, if the, like, suppose some like car black hole are scattering, like, which has some spins, then like we can show that, like, the spin, like this omega log omega term in the gravitational waveform, which turns out in the memory like 1 over u squared tail, and this, like, it predicts the 1 over u squared tail in the gravitational memory for the spinning black hole scattering processes.
Okay. And for example, like um, I'm not able to see it from this expression, but the spins that you have are pretty general, right? Like in the sense that you don't need the spins to be aligned or something like that.
No. This is like pretty general. Like, this is just the like the classical spin of the objects and not aligned to any directions. This is the full classical spin.
Okay. So, but has anybody taken this conjecture and really worked out the 1 by u square piece after the converting and so on?
No, actually, yeah. So this conjecture has not been appeared till now any paper. So this is like, we just have written down this conjecture, and like we are almost like trying to derive it. So we mostly have derived it, but we are getting some extra contributions, and we are trying to fix it, and then we'll write up the paper. So this has not been appeared yet.
Okay, so you're trying to derive the 1 by u square piece. So you think you can derive the 1 by u square piece from here and
Exactly.
make it as a statement about the waveform itself.
Yeah, for the spinning object scattering. Yeah.
Okay, good. Okay, thanks.
Thank you. So yeah, now let me talk about like how to derive this gravitational waveform without making any reference of the soft theorems from the S matrices. So this is what we are talking about as classical soft theorem. So the setup which we are considering is like, consider some m number of particles are coming in with momenta p1 prime to pm prime, and they are going through some complicated interactions within certain region of space-time. Let's call it curly r, and then they disperse to n number of objects with momenta p1 to pn, and also they can carry the spins also, like so we can tell the initial and final spin of the objects which are scattering. And inside this region R, we don't know, what happens is that the interactions could be very strong and anything, we are not aware about this thing. And suppose this region of space-time has a length scale which is L. Then with this setup, we want to derive the gravitational waveform at large retarded time u, and only we can, if we ignore the interaction inside this region, or only we can derive the gravitational waveform u when the u is much less than L. The gravitational waveform with retarded time u is much greater than L, which turns out to be determining the gravitational waveform with frequency which is much less than the L inverse. So this is like, with this setup, how much we can do. And this is what we are going to do. And what we assume is that, like, outside this region are only long range gravitational forces are present. If they are charged particles, then obviously one have to take care of the long range electromagnetic forces, but we are ignoring for a moment. Okay, then what we want to derive is basically the gravitational waveform. So let me define this h mu nu, which is the fluctuation of the metric, which is basically deviation from the flat metric, is defined in such a way. And then the E mu nu, which is the trace reverse metric, is defined in terms of the H mu nu. And then to derive the gravitational waveform, what we have to do is basically we have to solve the Einstein's equation. And in Einstein's equation, in this linearized form, in the de Donder case, basically looks like box of E mu nu equal to minus 8 pi j T mu nu. And this T mu nu has both like the matter energy momentum tensor part, which are determined by the trajectory, spins, and other structures of the objects. And this th mu nu is determined completely by the gravitational energy momentum tensor, which is for a Einstein gravity. This is basically like the Einstein tensor minus the linearized piece, which is written in the left hand side. This is the definition of the gravitational energy momentum tensor. And then we want to determine the time Fourier transform of this trace reverse metric fluctuation E mu nu, which is defined here. And if we want to determine the waveform at large distance, where r is large, then it turns out, and small frequency, then it turns out that it is enough if we determine the full Fourier transform of the energy momentum tensor, because like this E tilde mu nu is proportional to this Fourier transform of the T mu nu piece. So So the goal will be now to derive this Fourier transform of the T mu nu and like just put it in this expression, and we can read of the gravitational long wavelength large distance gravitational waveform, or the radiative mode of the 1 by r. So this is the radiative mode of the gravitational waveform. And to do that, let me tell a little bit how the matter energy momentum tensor will look like. So the matter energy momentum tensor outside this region R can be approximated by this expression, where you can see the first term in the matter energy momentum tensor is nothing but coming from just a point particle world line action. And the second term, if the particle carries spin, then the second term turns like coming from the spin part. And also there would be higher correction, like, and you can see if you compare the first term and the second term, the spin dependent term has a derivative over the delta function, which basically constrains the trajectory, like when x is x a sigma. And if you try to include the structure of the scattered object, then it turns out that the higher corrections contains more derivative over the delta functions. So if we try to, now what happens is that what we want to determine is the Fourier transform of this Tx alpha beta, and you can see due to more derivative over the delta functions, the Fourier, if we try to derive the Fourier transform of this energy momentum tensor, that contains more power of k, which is more power of omega. So if we like it at any order, if we try to derive only the first few non-analytic terms, like at least the first two non-analytic terms, then only this, if we only keep these two terms, that would be enough. And if we try to only derive the first non-analytic terms at each order in the omega expansion, then only the first line of this energy momentum tensor will be enough. So like these derivative expansions will tell us that like which terms we have to keep if we want to derive like what terms in the gravitation, like in omega expansion, how much order we want to proceed. So this is what I want to tell. Okay. And also then like one have to also take care of the trajectories of the particles, because like one have to derive this energy momentum tensor, we have to substitute the trajectory of the particles. So in this gravitational background, how the trajectory of the particles will look like. So if one can, so that like this is the geodesic equation, and if there is no spin, one can identify that this is the left hand side is 0 is the geodesic equation. But if the particles carry spin, then one can see that there will be spin correction in the geodesic equation, which is in terms of the two derivative of the spin and the Riemann tensor coupling to the spin. And if there is structures also, they will appear in higher orders. And also the spin have a time evolution equations. These are derived long ago by these people, MP and Dixon. Sorry. And then then what happens is that if we want to like, let me for a moment, if we just focus that at each order in the small omega expansion, we want to only derive the leading non-analytic pieces. So for that moment, we can then forget about the spin part, because in the spin part appears more derivative order. And then what boundary condition we have to fix. Like what if the scattering event which we are considering is basically some particles are incoming and some particles are outgoing. So we want to give the boundary conditions such that asymptotically the particles have a constant velocity, which tells us that dx mu d sigma have to be vmu, and that have to be specified for both sigma equal to plus infinity and sigma equal to minus infinity. And also like if we want to go, and also like whatever we have defined here in this structure, that when the particles are entering this region R, they are entering in at certain point. So at sigma equal to 0, basically that denotes these points, which are denoting by RMU. So in the trajectory, this is another boundary condition, that xmu sigma equal to 0 is RMU. If we try to derive also the spin dependent piece, then it turns out that asymptotically they have a constant piece. So that boundary conditions is also needed. But for a moment, we can just keep, we can forget about the spin part, just to give a general picture. And then what will be the strategy? The strategy will be that like we will basically iterate this process. Like basically we will try to solve the Einstein's equation to find the metric, and then use the metric as background to correct the trajectory of the particle, solving the geodesic equation. And why this is true, or can be done as a G expansion, because what happens is that in C equal to 1 unit, Gm omega, m is the mass of the scattered object and omega is the frequency of the gravitational radiation, turns out to be dimensionless quantity. And similarly, if one includes the spin, it turns out that G sigma omega square is a dimensionless quantity, and that is why it tells us that like the spin dependent piece will come at in higher order in omega expansion, because it is omega square. And similarly, if the r information which appears in the orbital part of the classical angular momentum, that also turns out to be in the omega square order. So what it tells us that, like, if we forget about the spin pieces and consider the particles as the point particles with any structureless point particles, and they also don't carry spin, then gm omega is a good quantity as an expansion parameter. If we want to expand in power of omega, that means we can expand in power of g. So that basically develops a iterative procedure as a like expansion in power of g, and we can iterate at each power of g and analyze this energy momentum tensor and then get the waveform and also the correction to the trajectories. So so what happens is that, okay, so let's, like, we started with the zero iterative order, consider the background to be flat, which is the mu equal to 0, and the trajectory of the particles asymptotically, they are basically straight lines like rmu plus bmu sigma, and then consider the corrected trajectory is basically in terms of ymu sigma, which is the deviation from the straight line trajectory, and then expand the correction to the trajectory, the Fourier transform energy momentum tensor, and also the metric fluctuation or the trace reverse metric fluctuation as a power series in G. And then, like, and we already know that how the energy momentum tensor and the metric fluctuation at each power of G are related. Then we just iterate to find out this delta. First order in iteration, we will try to find out this delta 1 ymu, and then using this correction to the trajectory, we again solve the Fourier transform of the energy momentum tensor, and we will iteratively proceed. So just to give an example, so yeah, let me skip these things. So just to give an example, like what happens is that at zeroth order, when the background is flat and the metric and the trajectory of the particles are straight line, the Fourier transform with the energy momentum tensor will take this simple form, and then we can use the relation between this waveform and the energy momentum tensor, and we can read up how the gravitational waveform at order G will look like. Then what we can do is that we can use this energy momentum tensor to compute the leading order metric fluctuation at order G, and then with this background in the first iterative order, we can basically try to get the first correction to the trajectory at first iterative order, solving the geodesic equation. And then once we get this, then at the first iterative order, we can write down the matter energy momentum tensor, which has this kind of simple form, and then we just substitute this expression and basically evaluate it. So this is like the first, and also at first iterative order, if we try to evaluate it, the matter energy momentum tensor will have this form, which, like, in a like we have just written it down as some derivative operator on the KGRCL, which I explained earlier. And also I have to analyze the gravitational energy momentum tensor at this order, because that is also order G. So that has the simple form. You can, like, only the quadratic piece of the metric fluctuation will be enough to derive that. And we have written, using the leading order background metric, we just have written down the gravitational energy momentum tensor. With this F is basically you can read off just from the Einstein's action the two derivative terms. That's why you can see those are quadratic in the momenta. And then you can substitute it and then evaluate different integration regions and try to evaluate how the gravitational like the energy momentum tensor Fourier transform will behave, and then add up, and you just use the relation to the radiative mode of the waveform to the Fourier transform, and you can derive the subleading order gravitational waveform, and this matches with the expectation which we talked about as a classical limit of the soft theorem. We also go to the next iterative order and also derived omega log omega square order, which is like similar to a two-loop analysis, and this also agrees with the conjecture which I made from the classical limit of the soft theorem. And currently we are working for the spinning cases, which is at order omega log omega order, to derive the spin dependent gravitational waveform. So yeah, I think I can also skip this. So now, like, this is what I talked about as gravitational waveform. Now I want to talk about what are the applications of this, and this is in terms of gravitational memories. So, like I talked about already, what happens, like the gravity, like the soft factors or the classical soft factors will look like in omega going to zero limit, like that tree-level result, which is the zeroth iterative order, which is the order omega, which is basically, it turns out that the omega inverse is basically the leading soft factor. If we do a Fourier transform, it turns out to be, this is a theta step function in U, and that means so like that u equal to minus, that there will be a difference between the gravitational waveform at u equal to minus infinity and u equal to plus infinity, and this is actually known as the gravitational leading gravitational memory, or the gravitational DC memory. But at one loop or order g square, which is the first iterative order, if one to analyze, then one finds the gravitational waveform will look like log omega, and at large time its Fourier transforms become 1 over u, which basically tells us that u going to infinity, they are not strictly just some constant value, but it's settled to the constant value with some power law behavior, which goes like 1 over u. And also like the order g cube order, which is also derived, that goes like omega log omega square, and in like large time it behaves like log u by u square tail memory. So like if one tries to do it for the leading non-analytic pieces, like for the n loop or the nth iterative order, one finds that the gravitational memory will look like log u to the power n minus 1 upon u to the power n. And these are exact at these orders in both loop order or the in power of the gravitational constant g. So this is the structure what we now got. And now just let me just flash the results, how they look like the leading gravitational memory, which is known from Christo W and like long ago. And this is like the leading gravitational memory, which is known and possibly like will be observed in near future. But with this also, due to this log omega corrections, we find like the gravitational tail memory, which is 1 over u, and importantly they are determined just by the momentum of asymptotic momentum of the scattered object. And also at subleading order, which is the log u by u square terms, that is also completely now determined, and this has the kind of structure which I am giving here. But don't look at the details, only the fact that they are completely determined by the momentum of the initial and final particles and the direction cosine from the scattering center to the detector. And also like if we consider the though still it is not completely derived, but the spin dependent tail memory will also behave like 1 over u square, and if the conjecture is true, then it will have the this kind of behavior. And we are trying to recently derive it, but somehow we are getting some extra contributions, we are trying to fix it, but this is what we expect from the classical limit of the soft theorem. And so let me finish by giving some interesting observations, and this is like really striking observations we have seen. So suppose like till now, suppose we have derived up to the sub leading order gravitational memory, which is for large positive u, the metric fluctuation e mu nu have a constant piece, have a 1 over u piece and log u by u square. And at large negative u, which is u going to minus infinity, it has a 1 over u tail and log u by u square pieces. And the coefficients we are denoting, suppose now focus on the large positive u, then the coefficient constant term we are calling a mu nu, b mu nu and f mu nu, which we have derived. Now like we are considering different limits, like different processes. So suppose consider the scattering of massless particles, like there is no massive particles, some massless gravitons are coming in, and like they are scattering to some another massless particles, and some gravitational wave is like these massless gravitons are high energetic, and some low frequency massless graviton or gravitational wave is emitting. So for that case, what happens is that this b mu nu, f mu nu and this c mu nu, g mu nu, which are the tail coefficients, tail terms in the gravitational memory, it turns out that they're completely determined by the initial momenta. Like so what it tells us that like if some scattering is happening, like only if you fix the initial momenta, this for the massless particle scattering, these are completely determined. You don't need to know what are the scattering angles, how they are scattering, any information. Initial momenta completely fixes the coefficient of the 1 over u and the log u by u square terms. And this is a little striking because like this is not true for the massless particles, massive particle cases, but for the massless particle case, it turns out that these terms are completely determined. And this mu term, which is the leading gravitational memory, and this is known that this cannot be like written just in terms of the initial momenta. It needs information about the final momenta or the scattering angles also, and this is what is known as the null memory. So that is why this term, determining this term, is complicated. On the other hand, this b mu nu, f mu nu, the tail terms are completely determined just by the initial momenta for the case of massless particle scattering. Even if some massless particles are coming in and they forms a black hole and some gravitational radiation, still this b mu nu, c mu nu are completely determined by the initial particles momenta. So this is one of the striking observation which I wanted to mention. And another observation is that suppose consider a gravitational scattering process where some massive particles are coming in and they scattered, and in the scattering process they form some massive objects and also some massless high energy gravitational radiation. And what happens is that these massless particles gravitational like radiation information in this 1 over u and the log u by u square terms can be rewritten completely in terms of the incoming particles information and the outgoing only massive particles momenta informations. So no, like the tail terms does not depends on if there are some like massless like gravitational radiation is happening or not, can be completely written in terms of the initial and the final particles momenta. And this is also one of the strange observation, and this somehow suggests that like if some like for a scattering process, and this is what happens in general gravitational scattering process, because suppose some two black holes are scattered or even like say supernova explosion is happening, always there are some massless gravitons will emit, high energy gravitons. But it turns out that the tail terms can be written only in terms of the massive particles information. So this is another striking thing, and this is not true for the leading gravitational memory. That tells us this tail memory are really in different nature than the DC gravitational memory. So just let me end giving some like order of magnitude estimations of some gravitational scattering process, like say core collapse supernova or hypervelocity star production or neutron star merger process, where there are more than one massive objects in the external states. These tail terms are non-vanishing and one can evaluate, and it turns out that the gravitational strain, which is basically the change of the length between the mirrors of the detectors relative to their original length, is basically turns out to be order 10 to the power minus 23, and which is in the age of the current gravitational wave detectors like LIGO. So like at least like in the future gravitational wave detector like LISA, one can observe these effects. But for the gravitational but for the black hole merger process, where only there is only one massive object, which is the only one massive black hole at the final state, it turns out that this u to the power minus 1 and the log u by u square tail term vanishes. And this is also one of the striking observations. What is the physical reason behind that we still have not understood. So the point which I want to make is that this observation of this vanishing or this non-vanishing gravitational tail memory will be a test of general relativity. And if we also can prove the spinning gravitational memory case, that can also tell us that if we can observe this 1 over u tail pieces, so whether the objects are carrying spin or not, we can differ also that observing the 1 over u tail piece. So let me thank you.
Thanks a lot, Biswajit. That was a nice talk.
Thank you.
We can unmute our mics and clap for Biswajit. And maybe we can take more questions.
I have a very naive question. If
Yep.
so, these tail terms can they be derived from full nonlinear general relativity just from asymptotic analysis or something?
And this gravitational memory.
Yeah, but not the nonlinear memory, but the tail terms that you're talking about, 1 over u squared.
I think it's possible. Like just analyzing the full nonlinear thing. But just I want to mention that like what happens is that you just see that if there are some massless gravitons are emitting, that information is somehow lost, and that terms can be completely expressed in terms of the massive object scattering. So yeah, I don't know whether like one can tell this tail terms as some nonlinear or null memory, like the way the leading terms has been expressed.
Okay, but so usually people do the expansion in the at null infinity, but if you have this, if you want to relate them to massive particles the way you're observing, then I don't know, you need some expansion of close to time like infinity or something.
Okay. So I understood your point. So like if there are massless particles, then since the reaches always null infinity, so like they to express this thing one needs the information about null infinity. But these tail terms are somehow suggesting that you don't need this thing, that you don't like, even if there are massless particles, still like just near like time like infinity, if you just consider the hyperboloid, and just in terms of that you can express this massless particles information.
Right, yeah.
This is what it is suggesting.
Yeah. All right. Thank you.
Biswajit, this result that you mentioned, that the waveform can be expressed. So if you have only massless particles, you can express it as just as a function of the incoming momenta. And you said if you have massive particles also, then you can express it as a function of the incoming massless particles momenta and outgoing massive particles.
Outgoing massive particles moment.
And you said you see this up to what order? So all
up to
the
log u by
subleading,
u square order, up to the
log u
subleading order.
And you expect that this sort of a result will hold even at further orders, or do you?
Yeah, that I don't know, like this, because like we don't have any general argument so that we can tell that it will hold to all order. So this is just an observations. Like after deriving this, if we take the limit of like some massive or massless particle, then we observe this.
So if you have some other way of understanding this,
yeah, there must be some other way of understanding, but yeah, we don't know yet how to understand this.
Right. That's very interesting. Do we have any other questions for Biswajit? And just to ask maybe on the same point, even if you, so that result remains true even if you had like electromagnetic forces or gravitation, this result holds true.
Even if there is some
both.
like even if there is some electromagnetic forces, still this observation is correct. Like this massless particles information can be completely incorporated with the massive particles information and the incoming particles information.
Okay, if there are no more questions, let's let me thank Biswajit again for this very nice talk. And thanks Biswajit, and I think I'll stop the recording.
Okay.